Hi, and thanks for joining us for Phosphorus Science Now. I'm Matt Scholz with the Sustainable Phosphorus Alliance. When confronted with trying to protect a water body from phosphorus pollution from agricultural lands, one of the challenges is trying to understand the exact source of the phosphorus. For example, is it from just applied fertilizer that's running off the land with precipitation, or is it from past fertilizer applications, so-called legacy phosphorus? The answers to these questions are important because they help determine how the pollution can most effectively be managed. For example, will inexpensive measures be enough, such as controlling application rates and timing to prevent incidental losses of newly applied phosphorus? Or will more expensive measures, such as installing phosphorus removal structures to capture legacy phosphorus downstream, be required? Researchers at the U.S. Geological Survey have been studying this very question across 173 watersheds in the U.S. They've recently published their findings in PNAS under the title Variable Impacts of Contemporary versus Legacy Agricultural Phosphorus on U.S. River Water Quality. I spoke with the lead author of that study, Dr. Sarah Stackpoole, to find out more. So Sarah, thank you so much for joining us for Phosphorus Science Now.
Thank you. I'm excited to be here.
Great. Can you tell us a little bit about your collaborators for this paper and where you got your funding?
So I worked on this paper with Ted Stetz and Lori Sprague, who are both scientists at the U.S. Geological Survey. And the funding was provided by the National Water Quality Program of the U.S. Geological Survey.
Okay, great. It's a very interesting paper. I'm interested in hearing what you have to say about it.
Great. Well, I'm excited to talk about it. The objective of our study was mainly to determine if historical phosphorus is a nutrient source to rivers and whether it is masking the effects of current conservation efforts. And this picture here is showing the Cayuga River in Independence, Ohio, and that was one of our river study sites. And so you might be wondering, why do we care about phosphorus in rivers and why do we care if it's historical or not? And so excess nutrients like phosphorus in freshwater ecosystems can lead to eutrophication. And that's a term that's used to describe explosive growth of algae and aquatic plants. And eutrophic waters have a variety of water quality problems, including dissolved oxygen concentrations that are very low, which cause fish kills and harm other aquatic life. So part of the motivation for this study was presented by looking at the results on the map on the right-hand side of this slide. Each circle on this map represents one of our U.S. Geological Survey river sampling sites. And the circles are color-coded in red and in yellow based on a total phosphorus concentration in the river relative to eutrophication concentration threshold. So literature has posited that 76 micrograms per liter is a threshold concentration. Anything above that for total phosphorus in a freshwater ecosystem is going to have a high potential for eutrophication. And what we found is that 60% of the sites in 2012 had concentrations that exceeded eutrophication thresholds for total phosphorus. And in 2012, having this finding, that was somewhat disappointing because many of the watersheds across the United States have actually had conservation programs that have been implemented for anywhere up to 20 to 30 years that were aimed at reducing the amount of phosphorus that is entering into rivers and streams. That can be either through erosion control measures or adjustments in the rate and timing of fertilizer and manure. So since reductions in current phosphorus sources have not produced great success in terms of water quality, many managers and scientists are turning their attention to other sources, and they're trying to determine if the mobilization of P from soils and sediments in these watersheds from historical inputs before a lot of these management practices went into place, if those historical inputs are having an impact on our nation's rivers' water quality. And so historical phosphorus is also called legacy phosphorus, and it can manifest itself in the environment in different ways. So on the left-hand side of this slide, I have illustrated in a cartoon scenario a couple of different ways that it can manifest itself in the environment. So phosphorus can desorb from soils derived from historical inputs, and this can happen long after the phosphorus is applied. And that's in scenario 1. And then in scenario 2, with continuous inputs of fertilizer and manure, traditionally reliable soil buffers of dissolved phosphorus can eventually be overwhelmed as a result of P sorption saturation, so that any additional phosphorus is more likely to run off. So that's shown in scenario 2. And then on the right-hand side of this slide is showing the various storage locations of legacy P. So legacy P isn't just stored in fields. It can also be stored in river channels, riparian and floodplain habitats, groundwater, and in lakes. And so moving on to the bottom right picture, the link between agriculture as a source of phosphorus and it being a source of a lot of the excess phosphorus and eutrophication has been really well established in the literature. And so what we tried to do in our study, and the unique contribution we feel, is that we could take a data set of agricultural phosphorus management on the terrestrial landscape. And what we did at the U.S. Geological Survey is link that to our national scale long-term water quality data sets to determine if legacy P was a source to rivers and streams on a national scale.
Yeah, and Sarah, you were able to actually find watersheds where agriculture was predominant, right? Where the wastewater treatment plants weren't the big sources. It was definitely ag.
Yeah, and that is a really important point to make. We removed watersheds from our data sets when we were looking at the river export if wastewater treatment facility effluent was more than 50% of the load. So the way that we evaluated agricultural phosphorus management was creating something that we called the Watershed Agricultural Phosphorus Balance. And that's defined by inputs and outputs, just like a bank balance. So two key inputs were fertilizer and manure, and one of the key outputs was crop uptake. In our study, the stream gauge location was used to define the watershed outlet. And at this stream gauge location and the watershed outlet, that's where we also estimated the river export. And that was done by coupling discharge and concentration measurements at that location. So here are some of our results. Using the manure, fertilizer, and crop uptake data from the Census of Agriculture, we estimated agricultural phosphorus balances for five-year time sets between 1992 and 2012. And so the time frame of our analysis was limited by the availability of Census of Agriculture data, which some of it is only available every 5 years. And then also we wanted to maximize the number of watersheds that we could use. And in order to maximize the number of watersheds, the time frame of our analysis was this 20-year period. And what we did is we averaged the five-year values to derive a mean watershed agricultural phosphorus balance. And then we used a t-test to assign each watershed to a balance category. So an A, the accumulation watersheds are all significantly greater than 0. And the depletion watersheds are all significantly less than 0. And not significantly different from 0 are the equilibrium watersheds. So for each one of our 173 watersheds, we estimated a mean agricultural balance. And the results of all of those watersheds are shown here, the mean values on the right-hand side. And 68% of the watersheds consistently had phosphorus surpluses ranging from 3 to 1,950 kilograms per square kilometer. 7% of the watersheds were in a depletion category, and the phosphorus balances ranged between -287 and -21 kilograms per square kilometer. And 25% of the sites were categorized as equilibrium, ranging from -140 to +350 kilograms per square kilometer. And this slide is using the same color coding strategy as the previous one. So the pink and the blue circles are indicating depletion and equilibrium watersheds. And you can see that these watersheds are located in rivers that are draining into Chesapeake Bay and to Lake Erie. And then the accumulation balance watersheds are distributed throughout the country. And both Lake Erie and Chesapeake Bay regions have been targeted for reductions in agricultural phosphorus inputs over time. So here we're talking a little bit more about the study approach, because the past few results slides have focused really on an understanding of phosphorus balances on the terrestrial landscape. Now what we need to do is link the terrestrial landscape to the rivers and streams, the water quality component. And many studies that have done this in the past have had access to really long-term data sets from both the water quality and the agricultural management perspective. Some of those studies have had data sets that are 60 to anywhere to 100 years long, and we did not have that. So what we had to do is develop a little bit of a different approach to look at whether or not legacy phosphorus is contributing to river export. So we used current data, and the current data is referring to the time frame 1992 to 2012, to determine if historical phosphorus, and that in our study is anything that any input into the watershed of phosphorus from manure and fertilizer before 1992 is impacting current water quality conditions. So we did that by developing this ratio. So the ratio, the denominator, is the mean agricultural balance, and you saw all of the results of those mean agricultural balances across the 173 watersheds. What we did is we related that to then the mean river export for the same time period. And Matt, this is the time frame of which we start not to be working with 173 watersheds. We're only working with 143. We removed the 30 because we found that the mean river export was influenced heavily by wastewater treatment facility effluent. So what we determined is if the mean river export, we found that that was always a positive value. So if the mean river export was in excess of the mean agricultural balance, we inferred that what was the phosphorus that was supporting the mean river export must have been historical phosphorus that was introduced into the watershed before 1992. And then if the current mean agricultural balance was less than 0, then the whole ratio would be less than 0. And since that what was supporting the river export, the current river export, must be the mobilization of legacy phosphorus in the watershed. So both of these ratios, either greater than 1 or less than 0, we assume that legacy P was contributing to river export. So then moving into this next slide, we wanted to actually estimate the % contribution of legacy export to the river load. And so the map here on the right is showing the results of that analysis. So if the ratio was greater than 1, we used this equation to estimate the % legacy P contribution to river export. And if the ratio was less than 0, we assumed that legacy phosphorus was contributing 100% to the river load. And we found that 49 watersheds fell into these two categories, and they're shown in various shades of pink in this map on the right. Anywhere between 1 to 100% of the river loads was affected by legacy phosphorus. Now, there's many more watersheds, all shown in white dots, that we could not estimate the legacy P contribution to river export because the mean agricultural phosphorus balances were so large relative to mean river export values, we couldn't distinguish what was the current versus what was the historical component to the river export value. So it's important to bear in mind, though, that even though the contributions of legacy phosphorus to these 94 watersheds could not be conclusively determined, a historical scenario of legacy P accumulation in these locations could have occurred. And it's just that using our methods, we weren't able to estimate that. But once these waters enter more of a depletion phase, the effects of legacy phosphorus could then be observed. So this last slide is a little bit different, some of the results here, than the results that I've been showing in the previous slides. So the previous slides are really focused on the mean values of the phosphorus balance and the mean values of the river export over that time frame of 1992 to 2012. What this slide is focused in on is the change in these two variables between 1992 and 2012. And so the color coding of the symbols relates to the agricultural phosphorus balances. So the brown squares in accumulation, pink circles are indicating depletion, and blue triangles are indicating equilibrium. And the shading is indicating, if they are filled in symbols, that legacy P contributed to river export. So you're looking at 143 watersheds on this slide. And the 49 watersheds where we determine legacy P contribute to river export are shaded in, they're filled in. So our results here in total do not show that management aimed at reducing or improving agricultural management. So the reduction in the agricultural phosphorus balances, so everything on the left-hand side of the graph here, produces consistent improvements in downstream water quality. So an improvement in downstream water quality would be indicated by a decrease in river export. And so what we see is on the left-hand side of this graph that is showing agricultural P balance decreases. We have nearly an equal number of watersheds showing river export increases. There are 43 watersheds in quadrant 1, and there are 48 watersheds in quadrant 4. And then looking at the right-hand side of the graph, in where P balance is increased over time, there were 33 sites with increases and 19 watersheds with decreases.
So it's really scattershot.
It is scattershot. And so even though we weren't able to have this linear relationship that if you bring down the agricultural lands, you're going to improve river export, there's a lot of meaning and value in the results that are shown here. And I'd like to kind of walk you through some of those findings or the importance of these findings.
Yeah, please do.
So let's look at Q1. So there could be a scenario where a manager or a farmer is looking at like, oh, well, I bring down my agricultural phosphorus balance over time. So I'm reducing the inputs relative to outputs in my farm or in my agricultural landscape over time. But whoa, I'm still seeing increases in river export. Oh, that must be because of this legacy phosphorus issue, right? It's something that happened before we put these conservation efforts into place. And Q1 is kind of dismissing that explanation here. There are some watersheds here close to the axis that have increases, and that the increases may be attributed to legacy phosphorus contributing to river export. But what you can see is a lot of the watersheds that are within Q1 are in an accumulation phase. So the agricultural phosphorus balance decreased over time, but there was still a surplus. And so much of a surplus, we couldn't distinguish if legacy phosphorus was actually contributing to it. But once these watersheds get into more of a depletion phase, we may see that the legacy impacts on contributing to river export. But another thing that we started to have to think about when we're looking at all of these different symbols is there's probably some larger additional factors that we weren't able to directly address that could explain the nonlinear water quality response to changes in agricultural phosphorus balances. And those two factors are best management practices and watershed buffering capacity. So watershed buffering capacity on a field scale can refer to the ability of soil to absorb additional P without contributing to river export. But you can also think of watershed buffering capacity as the entire watershed's ability to, on a larger scale. So the watershed's ability to absorb excess P in the soil, in the groundwater, or in the riparian areas. And then you can think about the best management practices as in-field management, such as vegetation buffer strips, cover crops, or reduced tillage. And sediment traps or constructed wetlands could be considered edge-of-field practices. So thinking about the context of best management practices and the buffering capacity, I'd like to look through some of these results again. Q1 versus Q4, they both had agricultural phosphorus balance decreases, but some had increases in river export and some had decreases. So one way to explain these differences is that a best management practice for the watersheds in Q4 could have been implemented around 1992 and have reduced the phosphorus transport from fields to streams and resulted in reductions in river export. And then if you look up at Q1 versus Q4 here, again, thinking about buffering capacity, there might have been some factor of the watersheds within Q1, their buffering capacity could have been reached and we could have passed the threshold upon which that watershed could absorb any of this excess phosphorus. And so that was exported into the rivers and streams, whereas there could be some element of buffering capacity here that the rivers did not demonstrate the increase in river export in response to those surpluses. So then also going over here into quadrants Q2 and Q3, we see that there's some watersheds here that had increases in agricultural balances with very little response to river export. And again, that could be reflective of a buffering capacity, but it also could be indicative of landscape management to reduce the amount of runoff of P from the field into the river or the stream. So in total, looking at the wide variety of results that are shown in this figure, we see that down here in the quadrant 4, agricultural management efforts to reduce agricultural phosphorus runoff through reductions in the P balance have been effective in improving water quality in some watersheds. But we can also see that there's increases in river export, and a lot of those watersheds still are in an accumulation phase, meaning that there are phosphorus surpluses. And so there's still additional strategies that are needed to promote adoption of nutrient conserving practices without compromising agricultural yields. And these practices need to be developed in the context of climate change, as heavy precipitation has been linked to enhanced transfer of nutrients from terrestrial to aquatic systems, and additional observed increases in heavy rainfall across most of the country are projected to continue. And therefore, the strategies to address phosphorus management as its source in the field are urgently needed now, as only a small amount of the phosphorus available in the soil solution needs to be transferred to freshwater ecosystems to cause a significant increase in stream water phosphorus concentrations and promote eutrophic conditions. And then third, we can see that legacy phosphorus is playing a role in increasing river export. And we can see that also in the symbols that are color-coded where we documented the legacy P contributions. But a whole nother level of all of these watersheds that are in accumulation phase, we weren't able to determine the total storage of phosphorus that are in these watersheds and what the impact of that is on the water quality. And so reductions in current phosphorus inputs are not alone not to reduce phosphorus, because those legacy sources will contribute potentially. And so what I think the take-home message is that most effective management strategies related to phosphorus and agriculture and water quality will need to be system specific and account for long-term effects of total historical phosphorus storage, as well as continuing to try to reduce the contemporary phosphorus surpluses. And then what we were able to also see is that further research to integrate information about watershed buffering capacities, so extending the time frame of our analysis to understand the buildup of phosphorus in many of these watersheds and how that could be influencing river export, would help us with management. And also an understanding of the spatial location of a lot of these best management practices, integrating that into our mass balance framework that we've already established would be helpful. And
yeah, that's great.
That is what I have, yeah.
So is that where you're headed with the research yourself, or are you leaving that for other people, looking into watershed buffering capacities and VMPs and how they fit into the mass balance framework?
I am looking into extending out some of the time frame for some of the watersheds to look at a longer time frame of water quality data. Phosphorus water quality data, they're in our national scale data set, we can probably go back to the end of the 1960s. And then ways to look at, agricultural phosphorus management going back into the 1930s and 40s. We're attempting to build up those data sets, but we have not done that so far. And then in terms of best management practices, those data are not integrated into a national scale data set at this time.
Okay.
Because some of that information is proprietary and it's field, it's attached to a specific site location. And so that's a gap in a kind of a national scale analysis.
Yeah, sure. And then is there a plan to keep monitoring these same sites in the same framework going forward?
Yeah, so the U.S. Geological Survey National Water Quality Program, there is going to be a continued effort to target long-term monitoring sites. The USGS will continue to be collecting data in terms of discharge and water quality at multiple locations across the US.
So Sarah, you define legacy phosphorus as phosphorus that was applied pre-1992, which, in traditional definitions of legacy phosphorus might consider phosphorus that was supplied between 1992 and today, much of that being legacy phosphorus. So can you explain a little bit about that decision and what its implications are for your study?
Sure, that's a really important point to understand about the approach that we use. So 1992, anything before 1992, defining that input of phosphorus into a watershed before that time, that year, is specific to our study alone. And that is based on the data that were available to us. So we used 1992 to 2012 as our current estimate, and anything before that would be considered historical input. But it's definitely true that a farmer on the landscape here in 2019, and they're trying to manage their agricultural phosphorus, that it might be in this outside of the context of our data and our study, that a legacy phosphorus may be considered something from 1992. But we only had water quality data up through 2012. That was our most current water quality data set. So that current time frame, 1992 to 2012, we're averaging all the information there of the river export, and we're averaging that with the agricultural phosphorus export. So those are the signal that we're looking at, and we're comparing those two things and calling that the current. And then if the agricultural phosphorus balance doesn't explain what we're seeing in the river export for that time frame, we're assuming it must have been some phosphorus that was introduced to the watershed outside of the time frame of our analysis.
Thanks so much, Sarah. That was a great presentation, and it's a great body of research. I'm really glad that you were able to join us today.
Well, thank you very much. It was great talking with you.